Now to solve this problem, we will separate the functions x, y, and z, and then we'll differentiate all of them with respect to time. Now this defines our x function, while this is y, and this is z. So we have x equals 3t cubed minus 2t, and then we have y equals 4t to the 1/2 plus t, and then for z we have 3t squared minus 2. We'll differentiate all of these with respect to time. So we have dx over dt is equal to, differentiating this, 3 times 3 will give us 9, and then 3 minus 1 will give us 2, so that will be our exponent. So 9t squared minus 2t will become 2. And then we have dy over dt, so this will be, let's multiply this to the coefficient, this will be 1/2 times 4 times t, and then to the power of 1/2 minus 1, and then t will just become 1. And then finally, we have dz over dt is equal to 3t squared will become 6t, and then minus 0. Or let's just remove that. And so since we want the particle's velocity, let's substitute 2 in all of these equations for the value of time. So we have 9 times 2 squared minus 2, and then 1/2 times 4 times 2 to the 1/2 minus 1 will give us minus 1/2, and then plus 1. And then for dz over dt, we have 6 multiplied by 2, which is 12. So this is now 9 times 2 squared minus 2. This will be 34, and then 1/2 times 4 times 2 to the negative 1/2, and then plus 1. This will be 2.41. And so to get the magnitude of the velocity, we have v equals, by the way, this is vx, this is vy, and this is vz. So this is now vx squared plus vy squared plus vz squared. We have square root of 34 squared plus 2.41 squared, and then plus 12 squared. This is now 36.14 meter per second, because we are talking about the velocity. By the way, this has minus right here. So essentially, the function of y has minus right here. So this is also minus, and then our ending result is actually minus 2.41. However, this won't change our answer, because if we will plug this into vy, we'll just square that, and then the square of a negative number will always be positive. So this is still the same. However, take note of this change. And so next, we need the magnitude of the acceleration. So we have a equals square root of ax squared plus ay squared plus az squared. Now to get the acceleration, we must differentiate velocity. By the way, this is for the velocity. So for the acceleration, we have, let's just label this x dot dot, which means that we'll differentiate this twice, or this once. So this will now become 9t squared will become 18t, and then minus 2, since that's a constant term, that will become 0. And then we have y dot dot, which is equal to, let's differentiate this function. Let's just write this again. Dotted y will be minus 1/2 times 4 will become 2. And then we have t to the minus 1/2, and then plus 1. And so differentiating this one more time, we have y dot dot, which is minus, let's multiply this to the coefficient, that will be minus 1/2 times 2t, and then minus 1/2 minus 1 will be our exponent. And then differentiating this, that will become 0. And so we have this as our function. And so this will now become minus times minus, that will be positive, and then 1/2 times 2, 2 will cancel. So we are left with t to the minus 1/2 minus 1. By the way, minus times minus was positive, and then 2 has cancelled. And so we have this. So this is t to the minus 1/2, and then minus 1. This is minus 3/2. And then for z dot dot, we have differentiating 60. We now have 6. And so let's substitute 2 in all of these components. So this is 18 times 2, which is 36. And then this is 2 to the minus 3/2, which is 0.35. And then this is still 6, because we don't have any variable. And so this is now a equals square root of 36 squared plus 0.35 squared plus 6 squared. And so we have square root of 36 squared plus 0.35 squared plus 6 squared. This is 36.498 meter per second squared. Now this is per second squared because we differentiated time twice. Or simply, this is the unit of acceleration. So we now have these values. Let's now try to solve this problem. Now we are given the velocity of a particle, which is along x 3, and then along y 6 minus 2t, so we have vx equals 3, and then vy equal to 6 minus 2t, where t is in seconds. And then we have the boundary conditions in which when r equals 0, t equals 0. Now we are to find the displacement of the particle during the time interval of t equals 1 up to t equals 3. And so since we are interested in the displacement, we actually need the position function. Now we know that the velocity is just equal to dr over dt. And so let's cross multiply. We have v dt is equal to dr, or simply dr is equal to v dt. Now we are given the boundary conditions. And so what this means is we actually have upper and lower limits for the variables r and t. So we will use these as the lower limits. So since we need to integrate this in order to get r, which defines our position, we now have the integral from the lower limit, which is 0, and then our upper limit is r of dr equals the integral from 0 to t of the velocity. Now the velocity is 3I and then plus 6 minus 2t j. And then we'll integrate this with respect to time so that we'll be able to eliminate the unit of time at the denominator. So recall that the unit of velocity is meter per second, and so if we'll integrate with respect to time, we can remove this. So we now have a unit of position. Now integrating dr, this will become r, and then since we have upper and lower limits, we essentially have a definite integral. However, using f of b minus f of a, wherein b is the upper limit and a is the lower limit, this integral will just become r minus f of a, so minus 0. This will just become r. So this is still our resulting integral. So we have r equals integrating 3i with respect to time. This will become 3ti, and then plus integrating this with respect to time, this will become 6t for this term, and then integrating 2t, we have minus 2t squared because 1 plus 1 equals 2, and then we'll divide this by the resulting exponent. So divide by 2, these will cancel, and then this is paired with j, and then since we integrated with respect to time, this will now be removed, and then instead of meter per second, we now have meters. Now since the lower limit is 0, then it won't change a thing if we'll apply the definite integral. So this is now actually our r, and so since we want the displacement between these intervals, we will substitute these values in our equation, and then we'll subtract them because we want the displacement. And so when t equals 1, we have r equals 3 times 1 of I, and then plus 6 times 1 minus, by the way, this will be removed. So let's just erase this. This is now only t squared. So we have 1 squared of j. And so this is 3i plus 6 minus 1 will give us 5. So this is 5j when time is equal to 1. And then when time is equal to 3, we have r equals 3t. So this is 3 times 3. And then I. And then we have plus 6 times 3 minus 3 squared for this equation, and then paired with j. This is now 3 times 3 will give us 9, so this is 9i, and then plus 6 times 3 is 18, and then 3 squared is 9, so minus 9. 18 minus 9 will give us 9j. And so the displacement will be, let's say, disp will be this vector subtracted by this vector, because this is at time equals 3 seconds, which is greater than 1. So we have 9i plus 9j minus 3i plus 5j. And so we will subtract these individually. So 9 minus 3, that will give us 6i, and then 9j minus 5j, that will give us 4j. So this is now 6i plus 4j. And then the unit will be meters. And so this is now our answer. Now for the next problem, we have a particle that travels along the parabolic path y equals bx squared, and then if its component of velocity along the y-axis is vy equals ct squared, determine the x and y components of the particle's acceleration. And then here, b and c are constants. So we are given vy equals ct squared and y equals bx squared. In this problem, we will actually use a combination of differentiation and integration. Now first, since we are given vy, we know that vy is equal to dy over dt. And so simplifying this, we have dy equals vy dt. And then just the same earlier, we will integrate this from 0 to t, y. And then on this side of the equation, we will integrate from 0 to t. However, we know that vy is equal to ct squared. So this will now become the integral from 0 to y of dy equals the integral of 0 to t of ct squared. So this is ct squared and then dt. So by integration, dy will become y, and then ct squared will become ct cubed divided by the exponent. So this is over 3. And so this is now our y. Now we are doing this to get the y component. So this is the y component, and then for the x component, we'll actually use a bit of simplification. Now we know that y is equal to bx squared. By the way, we need to define y as a function of time, and so that's why we didn't just use bx squared, because x is actually another function of time for the position along x. And so these components must be with respect to time. Now for x, we know that y equals bx squared. So y equals bx squared. But now we know that y is equal to ct cubed over 3. So let's change this. This is ct cubed divided by 3. So we can now solve x. We can divide this by b and also the other one. So this is over b. This will cancel. And then to get x, we can take the square root of both sides. So square root and square root. So we now have x equals, this will be removed. So x equals the square root of ct cubed over 3b. However, we can simplify this further by moving t cubed outside. Now since we are essentially taking the square root of t cubed, we can rewrite this as, let's move this outside. This will be t to the 3 halves, because this is now the numerator, and then the square root, since this is by default 2, this is now in our denominator. So t to the 3 halves multiplied by the square root of c over 3b. This now defines our x. So our x component is t to the 3 halves multiplied by square root of c over 3b. And so we now have both of these. Now next, we want to get the particle's acceleration. Now since we have vy, we can differentiate this automatically to get ay. So vy equals ct squared, and then differentiating, we have ay equal to, this will become 2ct, differentiating this with respect to time. So this is actually 2ct. However, for the x component, what we have is the position equation, or x. So that means that we'll actually differentiate twice. So we have x equals t to the 3 halves times c over 3b. By the way, this is just a constant term, so we can just actually treat this as a coefficient of t to the 3 halves. Now in our first derivative, we will be able to get vx. And so differentiating t to the 3 halves, we have t to the 3 halves minus 1, and then we'll multiply this here. This is 3 halves. And then paired with this constant value, so c over 3b. Now 3 halves minus 1 gives us 1 half. So this is now 1 half. And so now to get ax, we will differentiate this again with respect to time. And so let's multiply this to the coefficient. We have 1 half times 3 halves multiplied by t, and then 1 half minus 1. This is now our exponent. And then multiplied by square root of c over 3b. Now 1 half minus 1 will give us minus 1 half. And then 1 half times 3 halves, that will give us 3 over 4. So this is 3/4 multiplied by t to the minus 1 half times this constant term. So times c over 3b square root. So we now have 3/4, and then let's just move this down since the exponent is negative. So we have t to the 1 half. This is now at the bottom, so we will remove minus. And then essentially, t to the 1 half is just square root of t. So this is square root of t, and then multiplied by the square root of c over 3b. This is now the x component of our acceleration. So we now have this, the x and y components of the particle's acceleration. On to the next problem. Since we have already solved a lot of examples, let's just actually fast track this. Now we have the velocity equation, and then we have the boundary condition wherein the particle is at the origin when time equals 0. So we can just actually integrate directly. And then now we are to determine the magnitude of the particle's acceleration when time is equal to 2. Now since we have the velocity equation, we need to differentiate this. So we have v equals 16t squared I plus 4t cubed j plus 5t plus 2 k in meter per second. And so differentiating this, we have dv over dt, or the acceleration, that's equal to, this is 32t of I, and then plus, this will become 4 times 3 will give us 12, and then t, 3 minus 2 will give us 2, so this is j, and then plus, differentiating this, we have 5. And then pair this with k, we now have these components, and then this is in meter per second squared. And so to get the particle's acceleration when time is equal to 2, we'll actually use a equals ax squared plus ay squared plus az squared. So this is a equals, for ax, we have this function. So 32 times 2 and then squared plus our ay is 12t squared. Now, by the way, just to make this clear, these are our accelerations for each component. Now for ay, we have 12t squared, so 12 times 2 and then squared. And then for az, we have plus, this is only 5, so 5 and then squared. And so our acceleration is square root of 32 times 2 and then squared plus 12 times 2. By the way, this is actually squared inside because we have t squared, so this is squared. So 12 times 2 squared, quantity squared, and then plus 5 squared. So we have a value of 80.156. So 80.156 meter per second squared. This is for the first part of the question. Now for the next one, we need to know the x, y, and z coordinates of the particle at this instant. So for the position, we need to integrate this. Now integrating these separately, we have for x, this will be 16t cubed over 3. We are using the integration rule, which is x to the n will be x to the n plus 1 over n plus 1. So whatever the result of the exponent is, that will be our denominator. And then we need to add 1 to the exponent. So 2 plus 1 gives us 3. And then this is our denominator. And then our y will be, integrating this, we have 40 to the 4 over 4. So this will cancel. And then for z, we have, this will become 5t squared divided by 2. And then plus, we will now pair this with t. So 2t. These are now our functions. So substituting 2 for each, we have for x, 16 times 2 squared over 3. This is 21.3. By the way, this is actually cubed. And so this is now 42.6. Or let's say 0.67. So 42.67. And then for y, we have t to the 4th. So this is 2 to the 4, which is 16. And then for the last one, we have 5t squared, wherein t is equal to 2 divided by 2, and then plus 2 times 2, which is 14. So z equals 14. So our x, y, and z coordinates will be 42.67, 16, 14. This is now our answer. Now this next problem actually involves the integration of trigonometric functions as well as some identities. Now here we are given the equation of r, but the path is circular. So that's why we have the equation of a circle. And then we are also given the particle's velocity, which is Vy equals 2r cos 2t. However, that's still the y component. So since we know that Vy equals dy over dt, then we have dy equals Vy dt. Now we know that Vy is equal to 2r cos 2t. So this is 2r cos 2t paired with dt, and then we have dy. And then we'll integrate both sides. This is from 0 to y, and then this is from 0 to t. Now integrating dy, we have y equals, integrating 2r cos 2t. If we'll integrate cos 2t, we have cos 2t alone. That will be 1/2 sine 2t. And then we'll only integrate this function because we are integrating with respect to time, not r. So we will just actually leave this as is. So this is now 2r, copying this one, multiplied by 1/2 sine 2t. So this will cancel. And then we have y equals r sine 2t. Now if we will substitute this in our position equation, then we have x squared plus y squared equals r squared. And then we know that y is equal to this value. So this is x squared plus r sine 2t squared equals r squared. And then moving this to the left, we have x squared equals r squared minus r sine 2t squared. Now by the way, we are doing this so that we can get x, because we actually need the x component of the acceleration. So expanding this, we have x squared equals r squared, and then we'll square both of these because squared is outside, and then these are enclosed in a parenthesis. So minus squaring this one, we have r squared, and then multiplied by squaring sine 2t, that will be sine squared 2t. And so next, we will factor out r squared. So this is now x squared equals r squared multiplied by r squared divided by r squared will give us 1. And then minus r squared sine squared 2t divided by r squared will give us sine squared 2t. And so taking the square root of both sides, by the way, we can actually apply the Pythagorean identity right here. We know that sine squared x plus cos squared x is equal to 1. And so this means that cos squared x is equal to 1 minus sine squared x. Now this can be any variable or value. This can be 2x, 3x. As long as all of the values inside are the same, you can apply this identity. Now since this takes the same identity as this one, then we can actually change 1 minus sine squared 2t into cos squared 2t. So we now have x squared equals r squared, and then this will become cos squared t, 2t, because this is what's inside. So cos squared 2t, and then to get x, we will take the square root of both sides. So square root, and then square root right here, this will be removed, and then this will also be removed, all of these exponents. And so we have x equal to r cos t. However, since the root actually entails a positive root and a negative root, this is plus minus. Again, this is just the square root of 9 is actually plus minus 3. So we will consider the two values. So that's why we are writing plus minus. And so now, since we have Vy, which was 2r cos 2t, and then we have x, we can now differentiate this once to get the acceleration along y, and then we can differentiate this twice with respect to time in order to get ax. And so differentiating this, we have ay equals 2r. Let's just copy this because we will just differentiate with respect to time. So this is treated as a constant. And then cos 2t will become minus sine 2t multiplied by 2. So this is 4r, minus 4r sine 2t. So this is our answer. And then differentiating this twice, we have vx equals, this will become plus minus, and then cos 2t will become sine 2t, and then multiplied by 2 because we need to apply the chain rule. So this is now r, so we can simplify this into plus minus 2r sine 2t, and then differentiating once more to get ax, we have this will now become 2r, and then sine will become negative cos, but we still have plus minus, so minus cos, and then of 2t multiplied by the derivative of what's inside. So this is 2. So we now have ax equal to 2 times 2 will give us 4. So this is plus minus 4r times cos 2t. By the way, the negative sign here is just entailed in plus minus. And so this is now our answer. So ay equals minus 4r sine 2t, and ax equals plus minus 4r cos 2t. Now finally, we'll try to solve this problem. Now we have a box that slides down the slope, which is described by the equation y is equal to 0.05 x squared, unit in meters, where x is in meters, and then if the box has x components of velocity and an acceleration of vx equal to minus 3 meter per second, and ax equals minus 1.5 meter per second squared, when x is equal to 5, we have to determine the y components of the velocity and the acceleration of the box at this instant. Now take note here that we are interested in the y component. And so let's first write our equation. Now we have y is equal to 0.05 x squared. Now since we are given vx, we need to use implicit differentiation in order to find dy over dt and dx over dt. And so differentiating this with respect to time, y will become dy over dt, and then we have equals 0.05 x squared. We need to multiply this to 0.05. So 2 times 0.05, and then minus 1, this will now become x. And then since we are differentiating with respect to time, we will pair this with dx over dt. And so we can now get dy over dt, because we know that at x equals 5, the velocity is equal to minus 3. So vx equals negative 3 meter per second. Now this expression is just our vx. So this is vx. And then dy over dt is just simply our vy. So this is vy. And so now, we can substitute these values to get dy. Vy. So vy equals 2 times 0.05 multiplied by x, which is 5. And then multiplied by vx, which is minus 3. So we have 2 times 0.05 times 5 times minus 3. We have negative 1.5. So negative 1.5, and then this is in meter per second. And so this is now the answer to the first part, which is the y component of the velocity. So again, we have Vy equal to negative 1.5 meter per second. So this is our answer. Now to get the acceleration of the box at this instant, then we need to differentiate this twice. And so let's just actually copy this equation. And so differentiating with respect to time, we have dy over dt will become d squared y over dt squared. And then this is equal to 2 times 0.05. And then since this is a constant term, we'll just apply the product rule of differentiation for these terms. Now let me treat this as my u, and then let me treat this as my v. So we have our u is x, so we have x, and then our v prime is, since we are differentiating with respect to time, dx over dt will become d squared x over dt squared. And then we have plus vu prime, in which our v is dx over dt, and then our u prime will be differentiating x with respect to time, we have dx over dt. And so let me just move this. Since we know that this is the expression uv prime plus vu prime, we can just copy this, and then we'll multiply this by the constant term. Now recall that the second derivative of y and the second derivative of x is just the acceleration along that axis. And so d squared y over dt squared will become the acceleration along y, and also this one. This is the acceleration along x. So we have 2 times 0.05, and then let's copy x. And then this is now the acceleration along x, or simply the x component of acceleration. So this is x times ax. And then plus dx over dt will just become the velocity along x. So this is actually vx, as well as this expression. So we have dx over dt and then squared. However, since this is just equal to vx, let's just change this. This is now vx and then squared. Now let's try to look at our conditions. At x equals 5, we have vx equal to negative 3. So vx equals minus 3 meter per second. And then we also have ax, which is minus 1.5 meter per second squared. And so let's copy this, and then we will now plug these into our equation. Now this will become 5, and then this will be ax equals minus 1.5, and then our vx will become minus 3. So this is negative 3, and then we can now solve ay, or the y component of the acceleration. So we have ay equals 2 times 0.05 multiplied by 5 times minus 1.5, and then plus negative 3 quantity squared. And so ay will be 2 times 0.05 times 5 times 1.5, minus 1.5, and then plus negative 3 quantity squared. And so we have 3 over 20, which is 0.15. So this is 0.15 meter per second squared. This is now our answer.